Okay, let's go ahead and work some additional practice on the chemical equilibrium chapter. Again, this is looking at just kind of generalized chemical equilibria. So regular reactions, we're not focused on acid and base here. We're not focused on aqueous and anionic. Those are different chapters, so they will be different videos. But let's go ahead and spend some time on chemical equilibrium. As I start these questions, I'm probably going to go a little more in depth on a little bit of the background just to make sure that we're all on the same page again, just because I know everyone's at a different point in their studying. So if I am going a little too slow, fast forward to it, fast forward through it, put a different question, something like that, because I'm going to try to kind of re-explain some of those basic things we need for equilibria as we work through this first example. Okay, I've got suppose A is in equilibrium with B. First thing I want you to remember is that these arrows mean equilibrium. If I write an arrow like this is a general reaction. This is how we've been writing reactions to date, okay? So this is just saying this arrow that I've just drawn is just a straight reaction, reactant going to product. That's what you guys are used to. If you wrote the arrows like this is resonance. Again, not equilibrium. Equilibrium has a half arrow and a half arrow. That's intentionally stating that the reaction can go back and forth. Another thing is, in this reaction, we have A going to B. I know there's some confusion from students every year on this, so I just want to hopefully quantify or clarify that right now. We still say that A is the reactant and B is the product. Yes, the reaction can go backwards. B can react to form more A. In that case, B would be the reactant, A would be the product. But as written, A is the reactant, B is the product. And we write it that way so that we can communicate and that we can talk as scientists, okay? So we're still saying that A is the reactant, B is the product. We just understand with the arrows, the reaction can go back and forth. When I write these brackets, it means whatever inside, it represents their molarity. So me writing this is the same as me writing like, what is the molar in this one? 1.0, 1.00 molar. Okay, so it's the same thing. The brackets are a placeholder to represent molarity for us. We will also see some KP examples. In that case, we use, and I'll explain that again, but we use things like P sub A, which means the partial pressure of A. So atmospheres or torr, whatever we're going to use, usually atmospheres of A. Now that we got that out of the way, let's work the question. Suppose I've got A in equilibrium with B. At equilibrium, the mixture contained 1.00 molar A and 10 molar B. What is the value of Kc? Kc, again, is your equilibrium constant. And we find this by taking all of your products and putting them in the numerator. If they have any coefficients on them in the balanced reaction, they become the exponent on that species. If I have multiple components in the product, multiple things in the product, they get multiplied by each other. And Kc means we're using molarity because that C means concentration. Okay, so we're using molarity. And then your reactants go in the numerator. I call it the products over reactants equation, but that is simplifying it. I do have to remember that my products are being multiplied by each other. I do have to remember to include my coefficients. There doesn't happen to be any coefficients here. So my Kc here is just equal to the molarity of B over the molarity of A. Now it tells me that my molarity of B is 10 molar and my molarity of A is 1 molar. So my Kc value is just 10. Again, there's no units on Kc, okay? Even if there was, they would have canceled out nicely here, but they won't always cancel out nicely. And so there's no units on Kc, no units on Kp, no units on these Ks for equilibrium. And notice it's also a capital K. Lowercase k is reserved for things like when we write like kilograms or, any kilo thing, or when we're dealing with rate laws, which we will do in that kinetics chapter. What about this? This next part of this question here. If we added 2 molar A to the system, what happens? Well, some students want to say that my Kc must change, right? 10.0 molar divided by 1 plus 2 is 3, so 3.00 molar. So doesn't that just mean my Kc value is 3? And the answer is no, it's not correct. That's not what happens. We know that the Kc value is 10 here. It needs to keep that ratio at that temperature for this reaction. Kc is temperature dependent, but at that temperature, that Kc needs to change. So this is an example of Le Chatelier's principle. Basically, I have stressed the system. I'm going to draw it up here. I have A in equilibrium with B, and it was happy. It was at equilibrium. It had its nice little Kc value. I need to, now that I've disturbed the system, I need to let it adjust so that it can reestablish its equilibrium. I increase the concentration of A by adding 2 molar A to the system. And again, if I knew the volumes, that could correlate. Let's just assume 1 liter here. If we assume 1 liter across the board, then we can say we've added 2 moles, if that helps make it more sense to your brains. Initially, that concentration of A has increased. But when we're saying what happens, we're not saying like in that instantaneous moment. Equilibrium is not at the instantaneous moment. Equilibrium is once the system has recalibrated, what happened. If I increase that concentration of A, what's going to happen is some of that A is going to make more B because it wants to reestablish itself and reach the equilibrium it had before. It still needs that Kc value. Okay, this is the Kc value for this reaction at this temperature, for this reactant product. This system, this is the Kc value for this reaction at this temperature. So what's going to happen if I increase the concentration of A is the reaction will shift to produce more B. How much? Enough to get it back to that Kc of 10. And I didn't write this down, but you guys can do this on your own. I know that the Kc has to be equal to 10.0 molar. I know that right now my B is only equal to 10.0 molar. I've increased this to 3.00 molar. Now, I know it looks like you can't solve anything here. We can if we did a rice chart. So I'm not going to do it on this question because this was just talking about it, when it's saying what happens, I'm saying, explain to me what's happening here. So let's just tell you its principle. But I could actually go into here, change my concentration of A, knowing what C would be, I would find a new concentration. Sorry, where is it here? I'm looking for a different color. I'd find a new concentration here, and I could calculate this. Okay. Truthfully, I could even do it just here, but I guess I wouldn't need the full rice chart for that. We would normally, you could do a rice chart, but you could do it more simplistically. Find out what the new value is here. So what's going to happen when I change it up? Okay. Okay, yes, that math is easy comparative to what I could give you. I apologize. I'm tired. It's not even nighttime this time. It's morning and I'm still tired. But I hope that makes sense. So like this has to stay constant. This value has to stay constant because it's at that temperature. I've now changed this, which means this concentration is not going to be 10 molar anymore. It's going to change, it's going to react, or it's going to change comparatively to the A, but that is due to Le Chatelier's principle. Okay. But number two, for the equilibrium, 2 moles of SO2 gas reacting with 1 mole of O2 gas to produce 2 moles of SO3 gas. The Kc value is 278 at 25 degrees C. Calculate Kc values for the following reactions. Okay, so I've adjusted the reactions. Now again, some students have memorized how to do it. Like when I adjust a reaction, how do I change the thing? Most students will just memorize the patterns. I don't have them memorized. For me, it's easier to just derive them. I want you to figure out what's best for you. If you're unsure what I mean, go back to your notes for that one, okay? Or we'll look at one of the other videos where I go through that. Let's compare them. Letter A, I've got 1 mole of SO2 versus 2, a half a mole of O2 versus 1, and 1 mole of SO3 versus 2, which means that I multiplied this reaction by 1/2. I know that if I multiply through a reaction by 1/2, the new Kc value, which I'm going to call Kc prime, becomes the original Kc value raised to that power. So I've got 278 raised to the 1/2, which is the same thing as taking the square root. If you're unsure how to do this in your calculator, you can do two things. You can either take the square root of 278, or you can do 278, that little caret sign being raised, and then make sure to put this into parentheses, and it should give you the right answer. My Kc prime here is equal to 16.7. How about the next one? I've got 2 SO3 on the reactant side versus the product, 2 SO2 on the product side versus reactant, and 1 mole of O2 on the product side versus reactant. So I've reversed the reaction. I know from doing the examples and deriving it that if I reverse a reaction, I take the inverse of the Kc value, or I flip it. I take 1 over. So Kc prime here is 1 over Kc. 1 divided by 278. My Kc prime value here is 3.60, 10 to the negative third. I'll talk a little bit about what I mean, a little more about this in just a sec. Um, Actually, the next one's KP, so it's a good spot. What I want you to think about, it's hard for students to think about this, and the multiplying through one kind of helps students a little. I think the inverse one is a little easier, so letter B here is what I'm going to focus on. As written, the original reaction had 2 moles of SO2 reacting with 1 mole of O2 to give me 2 moles of SO3. And I saw the Kc value for that was 278. 278 is still absolutely in the realm of equilibrium, meaning I still have product present, but it is greater than 1, meaning it is product favored. Okay? What I did here was I reversed the reaction. As originally written, I know this reaction was product favored. So if I reverse the reaction, I expect the reaction to be reactant favored at this point, because now the species that was favored is on my reactant side. Okay, so I expect it to show reactant favored. And it does, mathematically, it does show it. But that's what the Kc is doing, even when I inverse it or reverse it like that, take the inverse. It's a comparison of product to ratio, to reactant to product. So because I've inversed that reaction, that Kc should also inverse. I should see that now what was originally product favored is now reactant favored. Okay, so the math is a comparable system there. I hope that makes sense what I'm trying to explain to you guys. But like the logistically, I expect it to go small now. If it was once product favored, I expect it to now be reactant favored. Okay, what about this one? Calculate Kp. Kp is only valid if you have gases. Okay, you can't use anything else in the equation, but you can use gases. And we do have a nice equation, which I need to zoom in here so I can write on the screen. We have Kp is equal to Kc times RT times the change in N. Again, R is your gas constant, 0.08206 liter atmosphere per mole K. I remember it's that gas constant because I know I'm dealing with pressures, and the other gas constant is dealing with energy. My temperature is in Kelvin, and the question tells me 25 degrees C, so 298 K. I know the Kc value because we've been writing it is 278. But that change in N, how do I get that change in N? Change in N is number of moles on the product side minus number of moles on the reactant side. If I look at the reaction, I have 2 moles of product, and that is specifically gas moles, okay? Specifically of my gases. If I have any other species in there, I don't count them. But I have 2 moles on the product side of gases because everything in here is in the gas phase, and I have 1 and an invisible 1 there, or sorry, 2 plus invisible 1. I have 3 moles there, so my change in N is equal to -1. I'm gonna go ahead and plug all of that into the equation in a color that isn't gonna blend in as bad. Let's see, my Kp will be equal to 278.08206 liter atmosphere per mole K times 298 K. And this quantity, the R and the T, is what's raised to that -1. Okay, so in my calculator, I do this calculation first. I then, when I get that answer, I hit the little caret and I hit, usually parenthesis on your calculators, -1, hit enter again, and then I times that whole thing by 278 to get the right answer. But I get 11.4 here. So we've worked through two of the problems. Let me take a break now. You've only got 28 more to go. Okay, what's this one? Le Chatelier's principle. Consider the following system at equilibrium. I've got carbon monoxide reacting with hydrogen to form methanol. I've got a delta H here that's negative. I don't much care what the value is, to be honest with you. It doesn't make a difference in this chapter what the value is. What matters is that negative sign. That matters. That tells me that this reaction is exothermic. Why exothermic? Because everything is described from the perspective of the system, and this means that the system lost heat. The system is negative. The system lost heat, that means heat is a product. So what will happen to the equilibrium concentration of methanol when, again, you guys don't know what methanol is yet. By process of elimination, you should be able to figure it out. You know carbon monoxide, you know hydrogen. So what's left is methanol, but just in case, this is methanol. And we're applying Le Chatelier's principle. The pressure of CO2 is increased. So if I change the pressure of CO2, CO2 is in a gas phase. I have increased the pressure here. What that has effectively done is increase the concentration because the pressure is related to that. Okay. So I've increased the pressure of CO2 in the system. That means I've increased the reactant side. But again, Le Chatelier is saying what happens to the system at equilibrium? It will reestablish that equilibrium. So if I increase the CO2 pressure, which increases its concentration, it will shift the reaction to form more product. What if I decrease the concentration of H2? Again, H2 is in the gas phase, so I am decreasing the concentration here. I'm effectively removing one of the reactants. Well, that's going to adjust by making more reactant. The reaction will shift to produce more reactant. The total pressure of the system is increased by the addition of helium gas. There's no effect here. Equilibrium is based on the partial pressures of the individual species actually involved in the reaction itself. So therefore, the partial pressure of helium isn't going to make a difference because it's a non-competing substance. The reaction mixture is compressed. When it's compressed, it's going to go to the side with fewer gas molecules because there's just less space for them. On the reactant side right now, I have 3 moles of gas. On the product side, I have 1 mole of gas. If I compress the system, that's increasing the overall pressure of the entire system. So it's going to move towards product formation because I only have 1 mole of gas on the product side. I increase the temperature. If I increase the temperature, I'm adding more heat to it. Again, this one really throws students off. It's like, but how would you add heat to something that's already hot? The system is giving off some heat. Yes, 90.7 kilojoules is nothing to laugh at. It is giving off a fair amount of heat, but that heat is part of that reaction. If I heat it up even more, add more to it, the system, it's not part of that reaction anymore. The system can't handle it. The system will take that back. And to adjust, it will go the opposite direction because heat is being treated as a product. It will shift to form more reactant. And a catalyst is added, again, no effect. Catalysts only find a different pathway for a reaction to occur by finding a pathway that has a lower overall activation energy than the pathway currently described or currently being used. And so the catalyst affects the reaction at the initial, but it doesn't affect the reaction once you reach the equilibrium. The equilibrium is its happy place. It doesn't need a catalyst anymore. It's already reached its goal. Number 4, Find Kc for the reaction given that Kp is 2.2 times 10 to the 12th at 25 degrees C. I've got 2 moles of NO plus 1 mole of O2 plus 2 moles of NO2. Okay, so I know my equation is Kp equals Kc times the product of RT raised to the change in N. I need to find Kc, so I need to algebraically reset this equation to solve for Kc. So therefore, Kc will be equal to Kp divided by RT raised to the change in N. And then it's just a plug and chug at that point. 2.2 times 10 to the 12th, 0.08206 liter atmosphere per mole K, 298 K. And then my change in N. Let's see what we've got. I've got 2 and 3 moles of gas on the product side, or sorry, reactant side. And I've got 2 moles on the product side. 2 minus 3 is a -1. All of that raised to -1. And my final answer here is 5.4 times 10 to the 13th. I forgot to say that earlier when I was talking about like how when I flipped the reaction, I saw that Casey went from, showing me a greater than one to less than one number. So like product favored to reactant favored. Here, my KP is definitely showing greater than one, so product favored. And I see my KC is doing the same. That should happen. If KP and KC, those should stay both favored to the same direction. So like again, if KC is equal to one, you are truly 100% at equilibrium. You have an equal amount of product to reactant. If KC is greater than one, you are product favored. That doesn't mean you don't have reactant present, but you are product favored. If you are less than one, you are reactant favored. And if you ever get confused, think about it mathematically, products over reactants, it gets you to the same point, okay? But if my Kp is greater than one, my Kc needs to be greater than one as well. Just kind of a little check to make sure you're doing things right. Okay, what about this one, number 5? The equilibrium constant is given for 2 of the reactions below. So I can see my equilibrium constant given for Kc um, of the reaction 1 and the Kc of the reaction 3. Determine the value of the missing equilibrium constant. Okay, so there's got to be something I could do to these two reactions to find what's missing. We're looking at Hess's law here. I'm going to compare the first reaction to the second one. I've got A moles. There's no A in the second reaction. I've got B. That's helpful. Got AB2. I got AB2. AB2 is on the wrong side. B is on the right side. It's not the right number of moles, so something's happening with B. And A is going to have to cancel out anyway, so I'm going to go ahead and flip this reaction around. I'm going to write it up here. That gives me AB2 in equilibrium with 1 mole of A and 2 moles of B. And I'm not going to write the Kc yet. I'm going to deal with that in a second because I want to make sure I got the reaction flipped correctly first. Comparing the second reaction, I got A again. There's no A in there. I got B, and B's on the right side still, but it was the last time and I had to flip it. Got AB3 and AB3. Okay, this one is set. I don't need to adjust it. I've got A gas plus 3B gas in equilibrium with AB3 gas. My A's cancel. 2 of my B's cancel, leave me 1 behind. I've got AB2 plus B giving me AB3. So again, if you need, I need to be able to write it. Sorry, I really can't write on the bottom of my screen. AB2 gas plus B gas giving me AB3 gas. That's what happened when I flipped the first one, kept the second one the same, but add them together. And I look, and it does in fact match, which is great. So the first reaction I flipped. So now I need 1 over that Kc value. The second reaction was what I'm trying to find. Third reaction, I kept the same, so my Kc value stays the same. But then I added the 2 reactions together. So what I need here is the product of the inverse of this and this value. I'm going to, for simplicity, call this Kc1 and Kc3, okay? And this Kc2. So Kc2 will equal 1 over 59, because I flipped the reaction, times 478, because again, when you add the equations together, you multiply the Kc values. This gives me a value of 8.1. So that middle reaction, I use the other two to find the middle reaction has a value of 8.1. What about number 6? The following boxes represent reactions of the type A going to B at equilibrium. In which of the following is Kc equal to 2? Let's just count it. Again, Kc means reactant, product of a reactant. And if I need a value of 2 here, that means I need twice as much product as I have reactant. In reaction 1, I've got basically 3 over 3, a value of 1. Not it. In reaction 2, I've got 1, 2, 3, 4, 5, 6 B's over 3 A's. I got 2. Let's just make sure we're correct. In reaction 3, I've got 3 B's over 6 A's. Not it. So reaction 2 is going to have a Kc value of 2 because I have twice as much product as I do reactant. Okay. Another Le Chatelier principle. The reaction, 2 moles of SO2 plus 1 mole of O2 is in equilibrium with 2 moles of SO3. Definitely seen that reaction recently. Delta H here is negative 198 kilojoules. And again, I don't have to, I'm not writing per mole here because this is 198 kilojoules as written like this, where this, let me emphasize what I'm trying to do here. This is my thermochemical equation. So that means that 198 kilojoules of heat is lost for every 2 moles of SO2 produced, is lost for every 1 mole, or sorry, of every 2 moles of SO2 consumed, is lost for every 1 mole of O2 consumed, is produced for every 2 moles of SO3 produced. So I don't have a per mole there because it's not per mole, it's dependent on the reaction. It tells me this reaction is at equilibrium. Okay. So how much will each of the following changes affect the equilibrium concentrations of each gas once the equilibrium is reestablished? Okay. My delta H is negative, so my heat is definitely on the product side. So plus heat over here. What happens if I add more O2 to the container? Where is my O2? I'm picking like the worst colors for these things. My O2 is here. If I add more O2 to it, that's going to increase the reactant concentration initially. The system needs to reestablish at equilibrium, so it will shift to make more product. So it's going to make product formation. What if I condense the system and remove the SO3? Hmm, okay, doing a few things here. So condensing means increased pressure, which favors side of less gas molecules. I look, I have 3 moles of reactant in equilibrium with 2 moles of product. So condensing it alone is going to favor product formation, but I'm also going to remove that SO3. So I'm going to remove the product. It's going to counteract that change by making more of it. It's actually a great way to encourage the reaction to go to completion. Remove the product as it's formed. Take it away. You can keep making it. If I just compress the gases, that's the same thing as condensing it. Okay, condensing the area, compress the gases. That's increasing the pressure. I'm going to make more product because again, I have fewer moles of gas on the product side than I do on the reactant side. What if I cool the container? Cooling the container is going to remove that heat. If I remove the heat, I'm removing a product, it is going to, again, make more of it. So I've cooled the reaction down. I've removed a reactant. It's going to increase, it's going to form more of it to replenish the stuff I've taken, the heat I've taken away. What if I double the volume of the container? Doubling the volume decreases the pressure. Therefore, it's going to go to the side with more molecules of gas and it's going to form reactant. If I warm the mixture, again, this is adding heat to it. So now instead of removing heat, I'm adding heat. When it does that, it's going to adjust itself by forming more reactant. It's going to go away. The heat is acting as a product, so if I've increased the product concentration, it's going to make more reactant. Adding helium to the container, there's no helium in the reaction. Helium doesn't react with anything, so no effect because it is a non-competing gas. It won't affect the partial pressure of the individual species. And adding a catalyst to the mixture, again, no effect. So again, catalysts affect getting to your equilibrium, but I'm already there. It doesn't care once you're there. It doesn't need to get there anymore. Number 8, at 35 degrees C, the K value is there it is, 1.6 times 10 negative 5. In an experiment, and that should be Kc. In an experiment, which 1 mole of NaCl is placed in a 2-liter flask, what are the equilibrium concentrations? Okay. Got 2 moles of NaCl gas in equilibrium of 2 moles of NO and 1 mole of Cl2. I need a rice chart. How do I know I need a rice chart? Great question. I know I need a rice chart because I have an initial concentration of one thing. It could even be an initial concentration of all things, but I have the initial concentration and I need to know the equilibrium concentrations. That's telling me I need a rice chart because I don't know exactly how much is going to react. My NOCl is the only thing I have present at the start. I don't have any of these present. They're not mentioned, therefore they're not present. And I know 1 mole in a 2-liter flask is the same as 0.50 molar if I figured out the molarity there. I don't know what the change is yet. That's what I've got to try to find out. But I know that this is a reactant, this is a product, and this is a product. So I'm going to do minus for reactants because they're being consumed, plus for products because they're being produced. But I cannot forget that I have coefficients up here. When it's a 1, it just stays X. But if it's any other number, we have to include it because 2 moles of NOCl react to produce 2 moles of NO and 1 mole of Cl2. It's not a 1-to-1 ratio, so I've got to make sure to pay attention to those coefficients. At equilibrium, this gives me 0.50 minus 2x, and x. My Kc value here is 1.6 10 to the negative 5. I write out my Kc expression, products over reactants, NO, but again, I cannot forget that 2 there. That becomes NO squared. Again, that's concentration of NO. Cl2, concentration, no exponent there because I don't have a coefficient up front. And NOCl in my denominator, also squared because of the 2 out front. But I just figured out based on my rice chart that at equilibrium, these are my concentrations. So I know this equals 2x squared for the NO concentration, x for the Cl concentration, and 0.50 minus 2x squared for the NOCl concentration. Now, I've not taught you the 5% rule yet. It is coming very soon. And yes, I realize I should teach it before now, but I never do. I don't know why. Um, it is coming soon. What the 5% rule is, I'll explain it now and you will see it in class soon. But I'm assuming that this value of x is so small that even when doubled, it won't have an effect on this. And so what I'm going to do is the way I write it is I say this goes to 0. It's the amount, here, the simple x or 2x, 3x, whatever it is, that I'm adding or subtracting to an actual numerical number. And I'm doing, so I'm trying to simplify the math here. I don't want to solve this thing as written. If I ignore this, this simplifies it to 2x squared. Sorry, 2x squared. I need to remember to square that 2 in the middle in a sec, times x over 0.50 quantity squared. So that's what I'm effectively doing. But I do have to check it to make sure it's correct. And I'll show you that in a sec as well. If I simplify that though, that makes my life a lot easier. That gives me 1.6 times 10 to the negative 5 is equal to 4x cubed. Again, the 2x squared here becomes 4x squared. And then I have the extra x here, so 4x cubed. Times 0.5, divided by 0.50 squared. I'm running out of space up here. 1.6 times 10 to the negative 5 times 0.50 squared, 4x cubed. I can solve for x now. So I'm going to solve this mathematically, divide by 4, and take the cubed root. If you're not sure how to take the cube root on your calculator, take whatever value you have, raise it, little caret, and say 1 over 3, and that is the cubed root, okay? But I solve this out, and I get an x value of 1.0 times 10 negative 2. Now, I haven't solved the question yet. This is just part of it. But I did use the 5% rule. So technically speaking, I'm supposed to check the 10% or the 5% rule. The way I do that is I make sure that the value I got for x here, so I'm trying to find the right functions, is insignificant enough that it can be ignored down here, that I can ignore it here. And so I'm going to draw it up here. The way I do that is I just check it. I say, okay, is 2x less than 5% of 0.50? Why 2x? Because that's what I ignored. Why 0.50? Because that's what I ignored it from. So 2 times 1.0 times 10 negative 2 divided by 0.50. And I didn't actually write this down, so 1 second. I don't know the actual number, I just know it's small. And then I multiply this by 100%. And the numerical value here is 4%. If that value is 5% or less, it is a valid assumption. It is not making, because it's just not making that much of a difference in our final answer. If it didn't, we would have to solve it with a quadratic formula, or worse, 'cause it's a cubed root, and or a successive approximation method. But it does work. It's within 5%, so I've ignored the x value. Let's actually solve the rest of the question though. Well, I want to know what the equilibrium concentrations are. So I just established, I'm going to just move this down. I've just established that my x value is 1.0 times 10 negative 2. So I'm going to plug that into the equation and solve for each species. That means at equilibrium, my NOCl value is 0.48 molar. Because again, I plugged it in. I have 2 of them, subtracting it from 0.5. My NO value is 2.0, 10 to the minus 2 molar. And my Cl2 value, 1.0, 10 to the minus 2 value. You don't have to keep those in scientific notation. You can put them in non-scientific notation. Just make sure that you write 0.020 and 0.010 because of sig figs. So 0.020 molar, 0.010 molar. That's fine too. But that was the 5% rule. I know I kind of went through it kind of quickly. We will see it in class a little bit more, but we'll use it extensively. But it just kind of simplified the math for me. I don't want to deal with successive approximations. I don't want to deal with the quadratic formula if I don't have to. Sometimes I have to, sometimes I don't. And if it's less than 5%, I don't have to deal with it. Okay. Let's see. Number 9. Carbon monoxide replaces oxygen and oxygenated hemoglobin according to the reaction. HbO2 aqueous plus CO aqueous give in equilibrium with HbCO aqueous and O2 aqueous. Okay. Using the reactions and associated equilibrium constants at body temperature given here, find the equilibrium constant for the reaction above. Let me get some actual space here. Okay, I gotta compare these reactions to the one above. I've got HB. There's no HB above. Not helpful. O2. O2's on the wrong side above. HbO2. HbO2's on the wrong side above. Pretty sure I'm going to be flipping that equation around. HB, no HB above. CO is on the right side above. HbCO, HbOC is on the right side above. Pretty sure that reaction is staying the same. Let's try it. Flip that first reaction around. I've got HbO2 in equilibrium with Hb plus O2. Second reaction stayed the same. I've got Hb plus CO in equilibrium with HbCO. Cancel things out. HB, looks like that's the only thing that cancels. Okay, HbO2 plus CO in equilibrium with O2 plus HbCO. That's correct. Good, we did it. So let's adjust our KCs. The first KC value, I reverse the reaction, so that means I need to flip KC. It's this value is equal to 1 over the original KC. So 1 over 1.8. I'm going to call this KC2. KC3 stays the same, 0.06. Okay, I'm adding the two reactions together, which means I need to multiply them. So I'm going to call this KC1, what I'm trying to find. KC1 will be equal to 1 over 1.8 times 306, which equals 170. I need two sig figs, so I'm rounding it to 170. I don't have any spaces. Sorry, you guys. Usually when I do your videos, I remake the slides and give myself space. Clearly did not do that for you guys this time. Okay, what do we have here? We have a nitrogen thing. Nitrogen monoxide is a pollutant in the lower atmosphere that irritates the eyes and lungs and leads to the formation of acid rain. There's a lot of words there. They are useless words. They're interesting words, but they're not helpful to the question at hand. So, nitrogen monoxide forms naturally in the atmosphere according to the endothermic reaction. N2 gas plus O2 gas in equilibrium with NO gas with a Kp value and at 298 K, this value. I may not care that it's endothermic. I just think it's interesting because that helps me if I ever want to deal with Le Chatelier's principle. Use the ideal gas law. Okay, I know that. PV equals nRT. To calculate the concentrations of nitrogen and oxygen present in air at a pressure of 1 atmosphere and a temperature of 298 K. Assume the nitrogen composes 78% of air. By volume, and oxygen composes 21% of air. Find the natural equilibrium concentration of NO in air in units of molecules per centimeter cubed. There's a lot going on here. Okay. First up, let's see. Let's assume we have 100 liters of air. Why not? We're trying to use the ideal gas law. We know 78% and 21%, so let's just do it in liters and assume 100, or assume 1 liter. Let's just assume 1 liter. Why? Because if I assume 1 liter of air, that means I have 0.78 liters of N2 and 0.21 liters of O2, and then I can solve the problem. I can find the number of moles pretty quickly because I'm given pressure and temperature of each species. So let's go ahead and do that. Number of moles of N2. I've got 1.0 atmosphere. I've assumed 1 liter, so 0.78 liters are nitrogen. My gas constant is 0.08206 liter atmosphere per mole K. My temperature is 298 K. So I've got 0.0319 moles of N2. My sig figs are here, so 0.032. Oftentimes I'll carry that extra number, but when I've got a 1 and a 9, I'm running it up to 2, I'm just going to move it and not have to carry the extra number around. That gave me the number of moles of N2. I'm going to have to erase this in a minute, but for right now, I can move this over. Do the same thing for oxygen. Number of moles of O2, 1.0 atmospheres times 0.21 liters, 0.08206 liter atmosphere per mole K times 298 K is going to give me 0.00859 moles of O2. I'm gonna go ahead and round that 0.0086 moles or yeah, moles. Ah, I need a rice chart in a second, but because this actually makes my life pretty easy because we assumed 1 liter, that means this is also 0.032 molar and 0.0086 molar because we have 1 liter. So that made our lives easier. If you need that information, you should go ahead and write it down because I'm definitely gonna have to erase that because I'm gonna need the space in a minute. I also was given Kp, but I'm gonna need Kc because I want concentration in each molecules per centimeter cube. So I'm gonna have to go through Kc. So I'm gonna do that down here. Kc is equal to Kp over RT change in N. If we zoom back out, my Kp is 4.1 times 10 to the negative 31. Gas constant, 0.08206 liter atmosphere per mole K. Temperature we know is 298 K. And that whole thing is raised to the, let's see what power. I have 2 moles of gas in the reactant side, 2 moles of gas on the product side. That makes it pretty easy. It's raised to the power of 0, which means Kc is equal to Kp. Because remember, I'm not dividing by 0. When something is raised, this whole quantity being raised to the power of 0, that means this whole thing is equal to 1. So Kc is equal to 4.1, 10 to the minus 31. Okay, pause it and write stuff down if you need to, because I'm definitely going to erase this whole thing right now. Okay, let's go ahead and set up our rice chart. N2 gas plus O2 gas in equilibrium with 2 moles of NO gas. Initially, I have, and I just erased it, of course, 0.32, 0.032, yes, 0.032 molar N2, and I didn't give myself enough space, and 0.0086 molar O2. I don't have any NO to start. My change, minus x, just an x because there's one of each, 1 mole of N2 and 1 mole of O2, so just x, plus 2 moles of NO, so plus 2x to count for those moles. This gives me an equilibrium concentration of 0.032 minus x, 0.0086 minus x, and 2x. My Kc expression is my NO concentration squared over N2 times O2. And I know that this equals 4.1 10 to the minus 31. I'm going to go ahead and plug in what I know, though, from my table. I know that NO at equilibrium. So again, I'll often forget to write this, but these are your equilibrium concentrations directly. If they were not at equilibrium, you'd be calculating Q, not K. So they are your equilibrium concentrations down here. So they're from the bottom of the table here. 2x squared for the NO concentration equilibrium. My N2 concentration equilibrium is 0.032 minus x, and my O2 is 0.0086 minus x. And I know this equals 4.1 times 10 to the minus 31. Again, I'm going to implement the 5% rule here because, well, I want to. I don't want to solve this thing. I'm going to assume that x is really, really small compared to 0.032 and 0.0086. So I'm going to assume that this is negligible and this is negligible. What that does, it simplifies the math. It gives me 4.1 times 10 to the minus 31 equal to 4x squared. That's just, squaring and squaring, divided by 0.032 times 0.0086. Hope you can read that on the end of the screen. And I'm going to solve for x. When I solve for x here, I get a value of 5.3 times 10 to the negative 18 molar. I could go ahead and check that 5% rule, but I can guarantee you x is very, very small compared to those numbers. If you are unsure, though, the way to check it would be take that 5.3, 10 to the negative 18, divide it by the smaller of the two numbers that you've ignored it from. Because if it's good for the smaller number, it's valid for the bigger number as well. Divide it by 0.0086 times 100%. That gives me a value 6.2, 10 to the negative 14. So if I ask you to check your assumption, that's how you check it. How much was x worth? How much did you ignore? And it was just a single x. I don't have to multiply it like I did the last one. It's not like multiplied by 2 or 3. And then divide it by what you've ignored it from and multiply by 100. You're representing the amount associated, the amount reacted compared to the start. My assumption is valid, so I was able to use the 5% rule. Okay, I know what x is, and what I'm trying to find is the concentration of NO in the air in units of molecules per centimeter cubed. So I know at equilibrium, NO is equal to 2x. I'm going to erase parts of this. I really need board space here. So I know that my concentration of NO, my molarity, is equal to 2 times 5.3 times 10 to the negative 18 molar, which is equal to 1.1 times 10 to the minus 17 molar. Now I've got to get these in the right units though. That's actually probably the easiest part of this entire question. 1 second, because I know that I do not have the actual answer written down. I need to look it up really quick because I don't actually have a calculator on me either. That'd just be too simplistic. When you're doing these things, though, I want you to think about how do I get to the units I need? I know the units I have, I know the units I want. How do I get to the right spot? And you guys should be able to do that without too much issue. I need number of molecules. I'm going to try to fit down here. Number of molecules per centimeter cubed. Okay. Right now, I have 1.1 times 10 to the minus 17. And that's from right there. Moles per 1 liter. How am I going to get to the right units? Well, I can work on the numerator or the denominator first. I don't really care. Let's go ahead and work on the numerator. What if I'm trying to get rid of moles? Well, I know that 1 mole of NO molecules contains 6.022 times 10 to the 23rd I know molecules, right? Avogadro's number came back. That got me my numerator though. That's cool. Now I just need to get to centimeters cubed. Centimeters cubed is a unit of volume. So is liters. I know that 1 liter is 1,000 milliliters. That cancels my liters. And I know that 1 milliliter is 1 centimeter cubed. Calculate that out, and based on sig figs, I need two sig figs, 6,400 molecules per centimeter cubed. I'm going to write that down here in the tiny little space we have. Actually, wait. Scribbling works so well when you're not trying to scribble. Okay, and my answer. That's a hard question. There's a lot to it. So I had to assume 1 liter that and use my percentages to find out how many liters of each gas I had. Use that with my ideal gas law, calculating that through to the number of moles of each species. Convert between KP and KC. Set up a rice chart. Use the 5% rule. Get it down to molecules per centimeter cubed. If it should not surprise you, this was a challenge question in either an old textbook we used or the textbook I used when I was an undergrad. I don't remember which, but it was definitely a challenge problem at one point. If you got it though, that means you're getting it. And that's really, really good. Because I know you guys can do these things. They just take a little bit of time. Let's look at the next one. I'm going to erase this stuff up here just in case I need space on this board. Okay. Consider the reaction Br2 gas plus Cl2 gas going to 2 moles of BrCl. The Kp here is 1.1 times 10 negative 14, 150 degrees C. A reaction mixture initially contained a partial pressure of 755 torr for bromine and a partial pressure of 735 torr for chlorine at 150 Kelvin. Calculate the equilibrium pressures of Br and Cl. Okay. I need to set up a rice chart. And so I've set up these slides so poorly to do that because I need to be, my rice chart includes that reaction. If you can hear the kittens, I really do apologize. They usually leave me alone all day, but now that I'm trying to record, that's all they want is my attention. Um, so bromine gas, Cl2 gas in equilibrium with 2 BrCl gas. Okay. Um, I need this in atmospheres. This is in torr. So rice charts, I know I told you guys that rice charts only work for molarity. That's true 95% of the time. They can also work with pressures. Because remember, your molarity is related to your pressure through your gas constant through your ideal gas law. So PV equals nRT, um, T being your temperature, R being a constant, and then, let me just write this what I'm trying to say. This can be rewritten as P equals N over V RT, but this quantity right here is molarity, which means that if I'm at the constant temperature and the gas constant's a constant, my pressure and my molarity are related to each other. So I can actually use pressure in these tables, but I do need them in atmosphere to be able to do that. So I'm going to have to find the number of atmospheres of each species first. Number of atmospheres of bromine, 755 torr. I know 1 atmosphere is 760 torr. So that gives me 0.993 atmospheres of bromine at the start. And number of atmospheres of chlorine. I'm given 735 torr. So of course no perfect square here. Can't be nice about it, huh? Um, 1 atmosphere, 760 torr. Too many letters there. Gives me 0.967 atmospheres. And I don't have any BRCl to start. So minus X, because they're reactants, and I only have 1 mole of each, plus 2X, plus, because it's a product, 2 because of the 2 in front, and then X is that placeholder, because again, I don't know how much is reacting. 0.993 minus X, 0.967 minus X, and 2X. Because I'm using pressures, I'm going to go ahead and use Kp. And the question did give me Kp, which is also nice and convenient. I'm going to shrink this down. I don't want to get rid of it yet. But I do need space. So my Kp expression, Kp is pressures, so it's the partial pressure of BrCl, which is my product, squared, over the partial pressure of Br2 times the partial pressure of Cl2. Again, they're not squared, triple, or squared or cubed or anything like that because they don't have a coefficient themselves. Substitute in what I have under the equilibrium here into my Kp expression. 2x squared, 0.993 minus x, 0.967 minus x. I am going to do the 5% rule here. So I'm going to assume this goes to 0, assume this goes to 0. That simplifies things for me. That gives me that 1.11 times 10 to the negative 4, which is the value for Kp, equal to 4x squared, again, squaring through this, divided by that 0.993 times 0.967. Solve for x and get an x value of 0.00516 atmosphere. Let's check the assumption, because what I mean by that is I'm going to check to make sure that what I did here is valid. To do that, I take that percent that I've ignored, that x value, and in this case, it was just an x. It wasn't multiplied by anything. And I'm going to compare it to the smaller of the two numbers, because again, if it's valid for the smaller number, it'll be valid for the bigger number as well. I've got 0.00516 divided by 0.967, the smaller of the two values, times 100%. That's driving me nuts. Is equal to 0.533%. So definitely valid. This is my check assumption. Definitely valid. But I still haven't answered the question because now I forgot what I'm doing again. Okay, calculate the equilibrium pressure of BrCl. Okay, my equilibrium is 2x. I just found x, which means I can find the equilibrium pressure. My pressure of BrCl at equilibrium is equal to 2 times 0.00516 atmospheres, which is 0.0103 atmosphere. And it doesn't say you have to, but if it did ask, that'd be the same as 7.844. It does not specify that I have to switch back to Tor though. So personally, I wouldn't, because it doesn't specify I have to. If it did tell me I have to go back to Tor, then I would. But if I don't, I'm not going to, because I'm not going to do more math than I have to. I'd rather move on to the next question. Let's look at number 12. So in number 12, I'm told at a certain temperature, the Kc value is 8.5 times 10 to the negative third. Reaction mixture at this temperature contains solid NH4HS, ammonia at 0.166 molar, and H2S gas at 1.66 molar. I want to know if more solid will form or if some of the existing solid will decompose as the equilibrium is reached. So I need to write these in the right spot. Let's see, ammonia 0.166 molar and H2S 0.166 molar. If I look at the Kc for this, the Kc expression is NH3 and H2S. And I really need to pay attention here because there's a solid here. And I forgot that when I worked this problem a little bit ago. So please make sure that you ignore it. Don't put your solids in your Kc expressions. They're solid. Pay attention to your phases. I get very used to just working gases in this chapter, and then I miss simple things. Don't miss simple things, okay? So that does not go into my Kc expression. But this also means my QC expression is the same. QC and Kc, difference is QC is at any point in the reaction. Kc is specifically at equilibrium. I don't know if I'm at equilibrium. In fact, by the way the question's worded, I'm probably not. I've got to adjust one way or the other to reach the equilibrium. So I'm going to plug this in for QC. I know each one is 0.166 molar. So let me check that because I don't actually have the math done. I don't know why I don't have this question written down anywhere. 0.166 times 0.166 gives me a value of 0.0276. So 2.76 times 10 to the negative 2. I'm going to compare QC and Kc. When I get Kc, I have 8.5 times 10 negative 3. QC, 2.76 times 10 negative 2. QC is bigger than Kc, so to reach equilibrium, I need to travel in the reverse direction. I need this reaction to go backwards to actually reach the equilibrium, which means that in order to reach equilibrium, I need more solid to form. So more of the solid will form to actually reach that equilibrium. Again, that's because I was able to calculate QC, because I'm under any conditions is QC, compare it to Kc. My QC is bigger, because 10 to the negative 2 is bigger than 10 to the negative 3 for the values, and therefore I need to travel backwards towards reactant production to be able to make more solid to actually reach. Consider the following equilibrium. 6 moles of NaCl were placed in a 2-liter flask and allowed to react until there was no detectable change in the concentrations of the reactants and products. At equilibrium, the flask was found to contain 1 mole of NO gas. Got the reaction. How much chlorine gas is present in equilibrium? What is the value of Kc for this reaction? Okay. I'm going to write the reaction up here just so I can set up the Rice chart. 2 moles of NaCl gas in equilibrium with 2 moles of NO gas and Cl2 gas. 6 moles were placed in a 2-liter flask. So 6 divided by 2 is 3, 3.00 molar. Allowed to react if there was no detectable change. Okay, so none of these present at the start. Minus 2x plus 2x plus x. 3.00 minus 2x, 2x, and x. Okay. At equilibrium, the flask was found to contain 1 mole of NO. Well, that's helpful. That means that the concentration of NO at equilibrium, which is equal to 2x, also equals, I need to write that so you can read it, 0.5 molar. Because again, 1 mole in 2-liter flask, 0.5 molar. But that tells me my X concentration, or my X value, is 0.250 molar. So how much gas is present in equilibrium? Depends on which one I want to look at. Let's see, how much chlorine gas? That's what I'm looking for. How much chlorine gas is present? 0.250 molar. What is my Kc value? I'm going to write this. Kc is equal to NO concentration squared, Cl2 concentration, and OCl concentration squared. This equals, let's see, my NO concentration is 0.5 at equilibrium, and it's squared. My Cl2 concentration is 0.25. And it's not squared or anything, so it doesn't have any coefficients. And my NaCl concentration is 3.00 minus 2x, which is minus 0.500 quantity squared. My Kc value here is 0.0100. So that's one answer. And then I think I don't know if I erased it or where I put it, but my Cl2 concentration equilibrium is 0.250 molar. Okay, consider the following equilibrium. I've got nickel 2 oxide solid reacting with carbon monoxide gas to form nickel solid and carbon dioxide. Delta H value is negative. Don't know what it is, but it's negative, and that's all I really care about. So I know it's exothermic, so plus heat. What will happen to the equilibrium concentration of nickel? I really need to change the slide, and I forgot about that. This should really say CO2. Nickel isn't going to change. It's a solid. It's not affected by the equilibrium. So I will try to remember to change that, but please change that in your slides, and I will try to update online for that to be changed. So that should definitely say for CO2. What if I increase the temperature? Okay, again, I'm going to be looking at CO2, not nickel, and I apologize. Nickel is not going to be affected because it is in the solid phase. So if I increase the temperature of the reaction, that's increasing the heat, that's going to throw the reaction towards the reactant side. That will decrease my concentration of CO2 because I'm making more reactant. I'm using up my product. Definitely need to change these things. I apologize. Let's ignore B because, or no, I mean, it doesn't do much. Like the equilibrium, this isn't a good question. I need to fix this one. I apologize. I definitely was not thinking about the fact that I had solids in here when I wrote this question, or I don't even know if I wrote it or pulled it from somewhere. Doesn't matter. Ignore B. C, the pressure of CO2 or CO is increased. If I increase the pressure here, um, let me back up right here really quick. If I did increase the pressure here, what would happen is I would increase the pressure here and the system would adjust by throwing it this direction. So it would undo whatever additive I have done to the CO, carbon monoxide. If I increase the pressure of CO2 though, I'm increasing the reactant. It's going to shift by making more CO2. So again, I would not ask a question like that. The mass of nickel oxide is increased. It is a solid. There's no effect. It's not going to affect my equilibrium. Total pressure is increased by addition of helium gas. No effect. It's a non-competing substance. And the total pressure is increased by compressing the system. I don't know what my moles of gas are. Let's see. I've got 1 mole of gas versus 1 mole of gas. I've got the same number of moles of gas on each side, so no effect because I don't have, neither side has fewer moles of gas. I apologize. I'll make sure to fix this one in your slides. But yeah, not written the best. Definitely need to find a different example or use a different species in the thing. I apologize about that. To throw something else out here, we could always say like, if I decreased the pressure of CO, what's going to happen? That'd be taking this away, which means I need to throw this reaction this direction. So that would decrease my concentration of CO2. Number 15, the equilibrium constant for the following reaction is 2025 Kelvin. And at 2025 Kelvin is 17.1. I've got HCN, which is HCN in the gas phase, plus a half mole of H2 gas, plus a half mole of N2 gas, plus carbon in the solid phase. Kc is equal to 17.1 at 2025. Cool. What is the value of Kc at the same temperature for the reaction shown below? Here I've got 1 mole of H2 gas, 1 mole of N2 gas, 2 moles of carbon solid, and 2 moles of HCN gas. So I have both doubled the reaction, I multiplied through by 2, but I've also flipped the reaction around. So my Kc for my new one, I need to flip the reaction. So 1 over 17.1, but I also need to square it because I multiplied through by 2. So my Kc prime will equal the reciprocal because I flipped the reaction, and then squaring it because I multiplied through the reaction by 2. Gives me a value of 0.00 342. Number 16. Consider the following gas phase equilibrium system. N2 gas plus 3 moles of H2 gas can be 2 moles of NH3 gas. If an equilibrium mixture of these gases contains 1.5 moles of nitrogen, 2.7 moles of hydrogen, and 4 moles of ammonia in a 2-liter vessel, what is the value of the equilibrium constant? So it's telling me that's the equilibrium mixture. Cool. That's easier. That means I just need to write my Kc. Kc is equal NH3 squared N2 H2 cubed. I have these moles in a 2-liter vessel, so I'll divide it by 2 basically. 4 moles of ammonia is 2 molar, 2.0 because of sig figs, 2.0 molar ammonia, and that quantity is squared. Nitrogen is 1.5, so 0.75 molar. Hydrogen is 2.7, so 1.35 molar. And I'm just not going to round, I'm going to underline that 3 to remember that my sig figs are there. And I'm going to cube that. And that gives me a value of 2.2. Again, I can plug them right into that Kp expression because I'm told this is the equilibrium concentrations. So I'm right at equilibrium right now. 17. Let's see. For the following reaction, Kp is equal to 0.262 at 1,000 degrees Celsius. Carbon, solid, hydrogen, gas, in equilibrium with CH4, which is known as methane gas. At equilibrium, the partial pressure of H2 is 1.22 atmospheres. What is the equilibrium? English is hard. What is the equilibrium partial pressure of CH4? Okay. My Kp for this is equal to partial pressure of CH4 over the partial pressure of H2 squared. This doesn't go into it, it's a solid. This equals 0.262. At equilibrium, my partial pressure of H2 is 1.22 squared. Solve that out, and I get 0.039 atmospheres. Number 18. I've got A plus 2 moles of B in equilibrium with 2 moles of C. At equilibrium, the mixture contains 4 moles of A, 1 mole of B, and 3 moles of C in a 1-liter container. What's my Kc? I'm at equilibrium, so I can just plug it right in. My Kc is equal to C squared over A B squared. 1-liter flask for each one, so that makes it nice and easy. C is 3 molar squared. A is 4 molar squared, and B, or 4 molar, and B is 1 squared. So 3 squared divided by 4 gives me a value of 2.25. Based on sig figs, I need 1. My Kc value is 2. What does that mean? It means it's product favored, but it's pretty close to an equilibrium. There's very little difference in there. There's still a lot of reactant in there because it's a really small Kc value, but it is product favored if it's greater than 1. 119, same reaction, new Kc value. I'm given a Kc value of 25 this time. A 1-liter flask contains 2 moles of A, 4 moles of B, 10 moles of C. Which statement is true? Okay, so it's telling me what the flask contains. I can figure out the concentrations there, but it's not telling me if I'm at equilibrium. That means I'm actually calculating Qc. Since it's a 1-liter flask, the numbers are direct. I've got C, my Qc is equal to the concentration of C squared over A over B. C is 10 moles in a 1-liter flask, so 10 molar squared. A is 2, and B is 4. Calculate that out, and I get 12.5. So what I'm doing now is I'm comparing QC and KC. I know my QC is 12.5. I did not write these in a great spot. I know my QC is 12.5. I know my KC is 25. KC is bigger, so it needs to travel that way to reach equilibrium. The forward reaction occurs. What that means is, as written, I need more product to reach the equilibrium. Number 20. Given these concentrations, A naught means initial, by the way. When I have that little zero down here, that means initial concentration. The initial concentration of A was 0.1, the initial concentration of B was 0.2, and the initial concentration of C was 0.8. Which statement is true? Well, I'm still doing QC. My reaction changed a little bit though. I've got concentration of C over A B squared. So initially I have 0.8 divided by my A, which is 0.1, divided by B, which is 0.2. A 0.2 is squared. This gives me a value of 200. My sig figs are here. So 2.0 times 10 to the second. That is definitely smaller than my Kc value though. So the forward reaction occurs. I need to make more product to reach Kc. UC is less than Kc, so I need to move forward. 21. Given these concentrations, which statement is true? I'm looking at QC again. I know QC is equal to the concentration of C, the concentration of A, times B squared. My C is 1 molar, my A is 1 molar, and my B is 1 molar. It's driving me nuts. And squared. I get a value of 1. UC is definitely less than KC. And forward reaction occurs. I'm seeing a trend here. That trend is about to end. Number 22. Students want to solve this mathematically, but you can't. They want to plug this in just like I just did. And then they see things, they're like, I divide by 0. I don't know how to divide by 0. I can't divide by 0. It's not defined. You're right. But it's because we're solving these questions mathematically without really thinking about what it means. What does this really mean? QC is telling me how much I have of something, and KC is telling me that this is how much I should have at equilibrium. It's the same reaction. A moles of A reacting with 2 moles of 1 mole of A reacting with 2 moles of B to produce 1 mole of C. And the Kc value is 300. But I'm told instead that I have no A present and no B present, but I have 1 molar C present. C is the only thing present. It needs to react to form, or decompose in this case, but react. It's going to decompose to form some A and B. The reverse reaction occurs. Can't be solved by math. Has to be solved conceptually. You have to think about it. You only have two of your species are missing. Two of the species on both your reactants are missing. The only thing that can happen is C will decompose. How about 23? I'm told that I have 1 molar A present. I don't have any B present. And I have 1 molar C present. I need some B. Nothing can happen until I get some B. The A is not important until some B shows up because C cannot be made without it. A reverse reaction will occur. What about number 24? 1 molar A, none of B and none of C. Students hate this answer, but some of these. No reaction can occur here. There's no B present to react with A. There's no C present to decompose to form some B. So therefore, no reaction can occur. It's none of the above. The reaction is not going to go forward. The reaction is not going to go in reverse. And the reaction is not at equilibrium because I don't have all the species present. No reaction will occur, so therefore none of the above. 25. 0.70 moles of NO2 gas was placed in a 1 liter container. When the reaction shown below had reached equilibrium, the concentration of NO2 was found to be 0.28 moles per liter. What is the value of the equilibrium constant Kc? Okay. zero point 0.7 moles in a 1 liter container means that my concentration is 0.7 molar. It doesn't mention these, so I assume I need to start. Minus 2x plus 2x plus x. Again, the 2's because of the coefficients, the 1 because of the 1 coefficient, minus for reactants, plus for product. I have 0.70 minus 2x, and x. But it told me that the concentration of NO2 at equilibrium was found to be 0.28 molar. That means 0.70 minus 2x has to be equal, that is driving me absolutely batty, to 0.28 moles per liter. Okay? So 0.28 molar. Again, that's 0.7 molar in that equation, so the molar shouldn't surprise you. If I solve here for x, that gives me a value of 0.21. But that means the value here is 0.42 and 0.21 because I just solved for x. Those are molar. Now I can solve my Kc. Kc will be O2 concentration times my NO concentration squared. Again, these are concentrations at equilibrium divided by my NO2 concentration squared. 0.21, 0.42 squared, 0.28 squared, definitely ran out of space. My Kc value here is 0.47. So I did still set up the rice chart, but again, I used it to help simplify it. I could do it without a rice chart, but it makes it a lot more simplistic to see it. 26, we're on the home stretch, 5 more. 250 degrees C, the reaction PCl5 in equilibrium PCl3 and Cl2 gas has an equilibrium constant Kc of 1.80. If 0.20 moles PCl5 is placed in a 5 liter container, what will be the equilibrium concentration of Cl2? Well, first, I'm told zero point 0.2 moles in a 5 liter container. So that means that the concentration here is 0.0400 molar. I'm not told anything about the other species. I'm going to write the rice chart above. 0.0400 molar, 0 and 0, minus x plus x plus x, 0.0400 minus x, and x. Kc is equal to PCl3, Cl2, PCl5. I know this equals 1.80 because the question told me so. And I know that these plug in here. So this is equal to x times x divided by 0.0400 minus x. I'm gonna have to use quadratic formula here, unfortunately, but it's fine. Calculator for x squared plus 1.80x minus 0.072 equals 0. And I'm going to have to use it because trust me, the 5% rule will not work if I try to ignore x here. How do I know? Because I tried it and it didn't work. And then I erased it and wrote down the right stuff. Solving the quadratic, I get two values. I get 0.039 or negative 1.8. I know that my value needs to be positive. I can't use the negative value. So I'm going to ignore the negative one and take the positive one. So 0.039. But that means that at what x is equal to 0.039. X represents the equilibrium concentration of Cl2. So that means at equilibrium, Cl2 is equal to 0.039 molar. And again, if I was to check that, 0.04 minus 0.039 leaves basically nothing behind. Definitely more than 5%. 27.600 moles each of N2 and O2 gas were placed in a 3-liter vessel, and the system was allowed to reach equilibrium at 3,900 degrees Celsius. What is the equilibrium concentration of N2? Okay, so it's 0.6 moles each in a 3-liter container. That's 0.2 moles each. Sorry, 0.2 molar each. Doesn't mention that at all. Minus x plus 2x. 0.200 minus x. 0.200 minus x and 2x. My Kc expression. NO squared and 2 and O2. Okay. I know that equals 0.0121, but that also equals is the equilibrium. I see. So let's set it up. 0.0121 is equal to 2x squared, 0.200 minus x times 0.200 minus x. I need to recognize that this is a perfect square. 2x squared, 200 minus x squared. It is a perfect square. Which is good, because I don't have to use quadratic formula, I don't have to use approximations. I can take the square root of both sides. When I do that, I'm going to get 0.110 is equal to 2x 0.200 minus x, and then it's just algebra. 2x is equal to 0.110 times 0.200 minus x. Make sure to distribute that through. 2x is equal to 0.0220 minus 0.110x. 0.0220 equals 2.110x. X is equal to 0.0104. What does x actually mean? Because once you get done with all the math, I don't know about you, but my brain gets tired and I forget what I'm actually doing. X down here correlates to the table. What am I trying to find? Because I definitely forgot. You give the equilibrium concentration of N2. So I need that 0.200 minus 0.0104 gives me 0.190. Those are all in molarity. So that means the N2 equilibrium concentration is 0.190 molar. I may not always write all my units and all the work, but I will write it at the end. You should write it at the end too if you want full credit. Definitely forgot to fix this. This should say K. A sample of pure NO2 is heated to 337 degrees Celsius, at which temperature it partially dissociates according to the equation below. At equilibrium, the density of the gas mixture is 0.520 grams per liter at 0.750 atmosphere. Calculate the Kc for the reaction. Okay. 2 moles of NO2 gas in equilibrium, 2 moles of NO and 1 mole of O2. Let's see. I've got a sample pure. I know the temperature. I don't care about that. The density is 0.520 grams and the pressure is 0.750. I can use that. Density equals molar mass times pressure over gas constant times temperature. If I can get the molar mass, I can use that, figure out how much I have of this thing. Let's see. Density is, I'm going to rearrange this equation for density. Sorry, I should emphasize what I'm doing. Um, dRT over P. So 0.520 grams per liter, 0.08206 liter atmosphere per mole K. Temperature is 337 Kelvin, which is 610, or 337 degrees Celsius, which is 610 Kelvin. Decimal place there for sig fix. That's very not straight. And the pressure is 0.750. 34.7 grams per mole. What am I going to do with all this information? Okay, so remember, what this is actually the molar mass of the mixture. So it's the molar mass of all these things added together. I don't actually know how much I have of each thing. So I'm going to use a placeholder. I'm going to say for the rice chart that I have A moles, or A for pressure. I'm using pressure here. I'm going to use KP. Um, I use A atmospheres of NO2 at the start. No NO and no O2. I know this is minus 2x, this is plus 2x, this is plus x. So at equilibrium, I have A minus 2x. And again, A is just a placeholder. I just can't use x, I'm already using it. 2x and x, okay? So at equilibrium, this is what I have. But I know that my total pressure is equal to the pressure of NO2 plus the pressure of NO plus the pressure of O2. Why do I know that? Dalton's law of partial pressures taught me that. Question told me that my total pressure was 0.75 atmospheres. So I'm going to substitute in from above. A minus 2x for the NO plus 2x for the or for A minus 2x for NO2, partial pressure, 2x for partial pressure of NO, and x for partial pressure of O2. And I'm going to simplify that. The plus 2x minus 2x cancels out. That gives me 0.75 equals A plus x. I'm going to isolate A, 0.750 plus x. So the pressure of NO2, 0.75 plus x, minus 2x at equilibrium. Sorry, that is a minus right there because I isolated it. Basically, I had to subtract x from both sides, so I subtracted it from the 0.75 to isolate the A. This gives me, at equilibrium, the partial pressure of NO2 would be 0.750 minus 3x. The partial pressure of NO is still equal to 2x, and the partial pressure of O2 is just x. Those are the equilibrium pressures based on the table above, okay? So just a little bit of algebraic manipulation there. Now, I definitely do not have space for this. Okay, we're going to erase this for space, and we're going to work over here. I know that my molar mass is 34.7 grams per mole, and I know what my species are partial pressure-wise at equilibrium. My molar mass of the entire mixture is equal to the mole fraction of NO2 times the mass of NO2 plus the mole fraction of NO times the mass of NO. Mole fraction of O2 and O2. Again, if I was going from 2 mole fraction, I'd be using molar mass to get there. But I don't know the mole fraction is the problem. I do know that the pressure of A is equal to the mole fraction of A times the total pressure of the system, though. So the mole fraction of A is equal to the partial pressure of A over the total pressure. I know they're partial pressures, and I know the total pressure. I didn't say this was a fun question, but I can do this. So with that in mind, I'm going to reset this equation. I'm going to say, okay, well, this is equal to the partial pressure of NO2 over the total pressure times the mass of NO2 plus the partial pressure of NO over the total pressure times the mass of NO plus the partial pressure of O2 over the total pressure times mass of O2. I apologize, those should be more masses there. So again, substituting this in to here, this in to here, this in to here. Simplifying this back down, or trying, P total times the molar mass will equal the pressure of NO2 times the mass of NO2 plus the pressure of NO times the mass of NO plus the pressure of O2 times the mass of O2. So all I did was multiply through the entire thing by P total. And this was molar mass was over here of the entire compound. So I just multiplied through the entire thing by P total to simplify the equation. Now I'm going to plug things in. I know that the total pressure of the system is 0.750 atmospheres. I know the molar mass of the mixture is 34.7 grams per mole because I used the density equation derivation from the ideal gas law with density. I know that my partial pressure of NO2 is 0.750 minus 3x at equilibrium, and I can add up the molar mass of NO2, and it's 46 grams per mole. I know the pressure of NO at equilibrium is 2x, and the molar mass of NO is 30 grams per mole. And the pressure of O2 at equilibrium is x. The molar mass of O2 is 32 grams per mole. I solve for x here, and I get 0.184. Still not done, but I'm closer. Now that I've done this through pressure, I can solve for Kp. Kp is the partial pressure of NO squared times the partial pressure of O2, because those are my products, divided by the partial pressure of NO2 squared. If you're unsure, go back and look at the original equation, like if you see it there, okay? I just need space to write. At equilibrium, I've got that 2x squared times x over 0.750 minus 3x, substituting in what I know x is the value of x now, 2 times 0.184 quantity squared times 0.184 divided by 0.753 minus 3 times 0.184, that should be squared, quantity squared. This gives me a value of 0.636, but that is Kp. And at this point, I've definitely lost track of what we're doing. I want Kc. Of course, I want Kc. Can erase it up here. So remember your equation. Kp is equal to Kc RT change in N. So therefore, Kc is equal to Kp RT change in N. Kc is equal to 0.636 divided by that gas constant, 0.082. 0.06 liter atmosphere per mole K. Temperature of this reaction, 337 degrees C, is 610 Kelvin. And it's that entire quantity that's raised to that power of 1. Why 1? Because it's number of moles of product minus number of moles of reactant. Got 3 moles of product versus 2 moles of reactant. So raise to the first power. My Kc value comes out 1.27 times 10 to the negative 2. So again, Kp was less than 1, Kc is less than 1. Remember, negative 2 doesn't raise to the negative 2 power, just means it's small. It doesn't mean that it's a negative number. That problem was a doozy. It's a big problem. That's definitely another challenge problem out of the textbook. Okay, let's look at number 29. Consider the reaction 2 moles of SO2 gas plus 1 mole of O2 gas, giving me 2 moles of SO3 gas. Kp is 0.355 at 950 K. 2.75 liter reaction vessel at 950 Kelvin initially contains 0.10 moles of SO2 and it should be a capital S, 0.10 moles of O2. Calculate the total pressure in atmospheres in the reaction vessel when equilibrium is reached. Okay, so this is that whole idea of adding up again. So P total is the pressure of SO2 plus the pressure of O2 plus the pressure of SO3. I know that I've got 0.1 moles of each, let's see, 0.1 moles of each reactant, and I don't have any product to start. So let's go ahead and set up our race chart. 2 SO2 gas plus O2 gas in equilibrium with 2 moles of SO3 gas. Got 0.1 moles. I've got a 2.75 liter system. I definitely need pressure here. So I'm going to have to find the pressure quick because I don't want to set up the table in pressure. I want to set the table up in atmosphere. I want to set the table up in pressure, not in molarities. So my pressure of O2 will actually be equal to my pressure of SO2 because I have the same number of moles. They're in the same condition. I've got 0.1 moles of each one, 0.08206 liter atmosphere per mole K for my R value, 950 Kelvin for my temperature, and the volume here is 2.75 liters. This gives me 284, I think, no, 2.84, can't read my own writing, 2.84 atmospheres. Okay. So again, that's just taking that moles, taking the gas constant, the temperature, and the volume I'm in, and giving me my pressure right away. I want pressure right away because since I'm trying to find the total pressure of the system, I'm going to set that rice chart up in pressure in the first place. So I have 2.84 atmospheres of each. 2.84. I don't have any SO3 to start. Minus 2x, minus it's on the reactant side. X is the placeholder, and 2 because of the coefficient out front. And minus x, minus because it's a reactant, no coefficient out front, so just 1x. And then plus 2x, again, plus 'cause it's a product that's being formed, 2 for that coefficient out front. At equilibrium, I have 2.84 minus 2x, 2.84 minus x, and 2x. I am told that my Kp value is 0.355, so I can solve this. I'm going to move down here. Kp is equal to 0.355, and based on the equation, this is the partial pressure of SO3 squared divided by the partial pressure of SO2 squared and then O2. So, but I just found from my rice chart above what those values should be. So that's what I can plug in here. Okay. So let's see if I can adjust that to do it. That means I've got 2x squared in my numerator. She might do the update. I think Siri will be more helpful, and she's just not. I've got 2.84 minus 2x quantity squared times 2.84 minus x. And I'm not squaring that because that's the oxygen. I'm going to zoom in and try to solve this. Now, I don't want to deal with that x. I'm going to assume this goes to 0. Assume this goes to 0. I'll check the approximation in a sec. Maybe I'll get lucky. This simplifies it to 4x squared divided by 2.84 squared and 2.84. If I solve for x here, I get 1.43. I don't know how to tell you, but our approximation did not work. 1.43 is definitely not less than 5% of 2.84, let alone when it's multiplied by 2. No approximations for us. This one I definitely went to the internet to solve because it gets messy. I get 4x squared equals 0.355 times 2.84 minus 2x squared. What I mean is I had to solve a cubed root, and I don't remember how to solve cubed root, so I had to use the internet to find that equation. It's been a while. 2.84 minus x. Get everything to the same side. Like, we're going to try to solve this thing. Negative 1.42 x to the cube plus 4.051 x squared minus 14.266 x plus 8.089. I actually don't know when I stopped talking because someone called and it cut off the video. So I hopefully got through this equation, this is where we were at, and then I plugged this in and solved it in a cubic equation calculator because I'm not going to do that myself. And I got an x value of 0.663. So plugging that in the end, my pressure of my SO3, sulfur trioxide, is equal to 2x at equilibrium, so 1.33 atmosphere. My pressure of my SO2, and I will zoom this all out and explain it in a sec, 2.84 minus 2x at equilibrium gives me 1.51 atmospheres. my pressure of my O2, 2.84 minus 0, or minus X gives me 2.17 atmospheres. So my total pressure, 1.33 atmosphere, 1.51 atmosphere, and 2.17 atmosphere. Overall, 5.01 atmosphere. So again, what I knew was that I had a 2.75 liter reaction vessel, 950 Kelvin. I don't care about except the KP had matched. It contained zero point 0.1 moles of SO2 and zero point 0.1 moles of O2. I needed the total pressure of the vessel when the reaction reached equilibrium. So the first thing I did was I took the moles of SO2 and O2. I circled those backwards. I apologize. SO2 and O2, converted it to atmospheres because I knew I was dealing with KP and I knew I was dealing with pressure. So I'm just going to set that rice chart up right in pressure in the first place. Set up my rice chart. I know I started with 2.84 atmospheres of SO2 and O2 and no SO3. Solve for equilibrium based on the reaction, and that's what I got there. I know that my KP is equal to the partial pressure of SO3 squared divided by the partial pressure of SO2 squared times partial pressure of O2. I plugged that in here and solved the equation. I definitely went and used an online calculator because I cannot solve the cubed root anymore. It's been a long time. But I solved that for X because unfortunately my approximation method wouldn't work because X was too big. Solved that through and I found the equilibrium concentrations of each one. But what I want in here is the total pressure. Therefore, I had to take advantage of Dalton's law of partial pressures. P total is equal to the total pressure of the system, all of them added together. And I got a final answer here, 0.501 atmospheres. So P total, 5.01 atmosphere. We are finally to the last example. Yes, definitely need some space. Okay, last reaction, or last question. The system described by the reaction CO gas plus CO2 gas give it an equilibrium of CO, Cl2. Gas is at equilibrium at a given temperature when the pressure of CO is 0.3 atmospheres, the pressure of Cl2 is 0.1 atmosphere, and the pressure of CoCl2 is 0.6 atmosphere. An additional pressure of Cl2 of 0.4 atmosphere is added. Find the pressure of CO when the system returns to equilibrium. Okay. I know that at equilibrium, I started with 0.3 atmosphere, zero point 0.1 atmosphere, and 0.6 atmosphere. So I can find my Kp pretty simplistically from that. Kp is the pressure of the CoCl2 divided by the pressure of CO times the pressure of Cl2. Nothing's squared because there's no coefficients on any of the reactants or products, so that part's kind of nice. I have 0.60 divided by 0.30 times 0.10. Overall, this gives me a value of 20. Decimal place is there. So my Kp value for this reaction is 20. Now I'm going to adjust it. I'm going to add something to it. I'm going to add, I forgot, I'm going to add some Cl2 to it, which means that I will still have 0.3 atmospheres of CO, but now I will have 0.5 atmospheres of Cl2, and then we still have the 0.6 atmospheres of CoCl2. But now I'm under new initial conditions. I need to reach the equilibrium again. Minus x plus x, 0.30 minus x, 0.50 minus x, 0.60 plus x. Kp, again, is the partial pressure of the CoCl2 divided by the partial pressure of CO divided by the partial pressure of Cl2. So, I know it's equal to 20. I'm going to plug in these equilibrium concentrations into this. 0.60 minus x divided by 0.30 minus x times 0.50 minus x, and that equals 20. I need space, and I don't have that. Okay, algebraically, this is the whole FOIL method that you guys learned more recently than me. But I'm going to go ahead and algebraically manipulate this. So I'm going to have 20 times 0.15 minus 0.80x plus x squared, 0.0 minus x. So distribute that 20 through that. That gives me 3.0 minus 16x plus 20x squared equals 0.60 minus x. Get everything to the same side because I'm going to have to solve a quadratic here. 20x squared minus 17x plus 2.4 equals 0. Solve that quadratic, and I get two x values. I get 0.67 and 0.18. Only one of these is valid. This is too big. I can't subtract something bigger than I'm starting with. So this is my valid answer. This is the only valid one. I'm going to pull this down. Remember, at equilibrium, this is what I said I had. And I now know that x equals 0.18. This was for CO, Cl2, and CoCl2. So my pressure of CO, I always never make that second O big enough when I'm doing just carbon monoxide. 0.30 minus 0.18 is adjusted to 0.12 atmospheres. If I cared enough to calculate the other two, my PCl2 would be 0.32, and my pressure of CoCl2 is 0.78. Let's ask ourselves, does that make sense? Does that question make sense to us, how that's worked out? Originally, we had a partial pressure of CO of 0.3. We added 0.4 atmospheres to it. Now, we had initial pressure of Cl2 of 0.1. We had initial pressure or equilibrium pressure of CoCl2 of 0.6. Now everything's adjusted. I added some reactants, so what's going to happen? It's going to form more product. And I saw that concentration increase of that product. So sure enough, I added more of it, and now it has adjusted, and it's gone and made more of that product. The CO concentration is decreased even more. That's another thing I should emphasize. It's decreased even more because what I added to the system was Cl2. So my Cl2 concentration has decreased a little bit from the addition, but it's a little bit higher here. It's higher than the initial because I added a bunch more to it, right? But my CO concentration has decreased a lot. Yeah, I'm too many letters here. I need to start calling their names. But my carbon monoxide concentration decreased a lot, which is what I'm trying to find, because I never added more of it. I just reacted a whole bunch more of it by adding more chlorine to the system. And my CoCl2, that definitely increased as well because when I added more of that reactant, it had to produce more product. I hope that all makes sense to you guys.